Hello, my name is Gavriel Habib, and I will present our paper, Watch Where You Head, a View Biased Domain Gap in Gait Recognition and Unsupervised Adaptation. I would like to thank all the authors, Noah Barzilay, Shimshi, Rami Ben-Ari, and Darshan. Can you guess who is this person based on his walking pattern? Well, it's pretty difficult, but given two options, can you guess which one of them is the correct person? According to state-of-the-art gait recognition model, the answer is number 2. But actually, the model is wrong. We will discuss later on what made it fail. First, let's define the gait recognition task. Given a query sequence of a walking person, we would like to find his other sequences in a predefined gallery. A gait recognition model sorts the sequences in the gallery based on their similarity to the query. In this example, the correct sequence appears first. Gait benchmarks are evaluated with rank 1, which is the accuracy of the closest match. Gait is a challenging task due to complex conditions, for example, clothes changing, object carrying, and diverse camera views. There are four famous datasets for gait recognition. CASIA-B and OU-MVLP are indoor datasets, in which the walking direction is predefined and several cameras capture the human in multiple views. Gait 3D and GLEW are more challenging datasets captured in the wild. The most common gait models use the silhouette representation for training. Existing gait models achieve high performance. The table presents the results of 3 gait models on 4 datasets. However, when a model is trained on the source datasets and tested on a different target dataset, the results deteriorate. The ability to generalize to new datasets is limited due to domain gaps. Domain gaps can be caused, for example, by different camera settings or clothing conditions. To reduce the domain gap, unsupervised domain adaptation can be applied. The idea is to transfer a model learned from a source domain with labeled data to an unseen target domain without labels. Suppose a simple example of a classifier trained on a source domain. Due to domain gap, the classifier doesn't fit to the target domain. UDA aims to adapt the classifier to the target domain without access to the target labels. Despite the necessity of UDA in gait recognition, only a few studies have addressed this task. Trandi attempts to close the domain gap by fine-tuning the source model with a neighborhood selection strategy based on entropy confidence measure. Effectively, its main effort is to keep bringing closer adjacent samples with high confidence of belonging to the same identity. From indoor to outdoor applies clustering and a pseudo-label strategy in the target domain. Now let's move on to our method. These are the key contributions. First, we reveal a fundamental bias in cross-domain gait recognition models toward viewing angle. View is defined by the camera position relatively to an individual's walking direction in the 3D scene. Second, we propose a UDA method named GOUDA to mitigate the observed viewing angle bias and to improve performance on the target domain. Third, we conduct extensive experiments outperforming prior state-of-the-art by a large gap. These figures show the distribution of gait representations color-coded by their viewing angles. In the source domain, left figure, the distribution is nearly uniform, invariant to views. In the target domain, the right figure, the clustered colors imply a strong bias toward the viewing angle. In the target domain, nearby points are likely to be from similar view and not necessarily the same identity. The view bias causes a significant drop in rank 1 accuracy. We show that GOUDA is capable of disentangling the view bias, modifying the embedding space in the target domain to improve the recognition accuracy. Here is an overview of GOUDA. At stage 0, we estimate a single view per each gate sequence in the target domain using its provided key points. We use a gate model pre-trained on the source domain as a feature extractor for the unseen target domain. In the embedding space, we apply our triplet selection algorithm to adapt the view distribution in the target domain. Practically, we push away sequences of similar views while bringing closer different views. Lastly, the selected triplets are used to fine-tune the network using triplet loss. Let's deep dive into the triplet selection algorithm. Without access to the target labels, we estimate the views and use them as cues for selecting the positive and negative samples. Suppose we have the following view distribution, while each shape represents a different view. Ideally, we aim to find correct triplets, such that, given an anchor, the positive sample has the same identity but a different view, and the negative sample belongs to a different identity but of similar view. The positive sample is chosen to be the closest sample with a different view. We assume that among all samples with different views, the ones with the same identities will be the closest, as the source model has a certain level of knowledge on general gate features. We would like to increase the certainty that the anchor and the negative samples don't share the same identity. Therefore, we choose the negative sample with a similar view to be the farthest sample, up to a margin. To increase the probability that the triplets are correct, we use curriculum learning. In each triplet selection stage, we select the top confident triplets for training, using a confidence measure. That way, we keep improving target domain performance by starting from updating the model with a small amount but high quality data, and carefully extending the dataset size. Self-supervised learning is also added on top of our triplet selection method. The positive sample is replaced by an augmented version of the anchor. We evaluate GOUDA on multiple gate backbones and datasets, showing superior performance compared to direct testing, which is the source model. In some cases, GOUDA improves the rank 1 by a significant margin. GOUDA significantly outperforms prior works in 9 out of 10 settings. The results are explained by the robustness of GOUDA to different views compared to TRAN-D. TRAN-D usually selects positive samples with the exact same view as the anchors, as it brings adjacent samples closer. Contrary to that, GOUDA selects positives with different views by definition. To summarize, a take-home message. Although the identities in the target domain are unknown, GOUDA is capable to improve the recognition performance by estimating the views and adapt their distribution. Thank you for listening. For more information, ablation studies, and analysis, please read the paper.